Hello, my name is Jill Wang, and I did P7 or root. So the root finding project is basically like a very primitive Google Maps. We have the data of all the major cities, um, and the highways that connect them in data, and we are tasked with creating an algorithm that can basically find the shortest the shortest path from like city A to city B. Okay. So today I'll be focusing on the implementation option one, graph representation and basic operations. And the key data structures I used was a map that maps a key set of a bunch of points to a list of a bunch of points, which are the values. And this map represents a graph. So a bunch of nodes and edges. But this specific um, implementation uses an adjacency list. Okay. So I'll be going over my method initialize first. All of this was given, but basically I did implement the vertex count for loop and the edge count for loop. So basically for like the amount of vertexes that there are, that the file tells us that there are at the very start, we will get the next line and then split it based on where the spaces are. And so that'll give us an array of strings. And so we will parse in the first double and the second double in that line. So it'll be index one and index two, because the index zero is just the name. And so this is the latitude, this is the longitude for our new points. So we can make a new point out of that. And then we're just adding it to the point list. And then we simply just add it to our graph as a new key with an empty array list as its value. The edge count is very similar. We're taking in as many edges that the program says, well, the data file says that there are, and we are saying, well, this time the name is second, so ignore that. But data 0 and data 1 will be like there will be edges to, or not edges, there'll be like other nodes that are adjacent to each other. So this means that data 0 and data 1 are two cities that are adjacent to each other. And so we add them to each other's adjacency list. And that's what my graph.get P1 add P2 and my graph.get P2 add P1. Okay. So now I will be, and I already went over the graph data structured as a map, like an adjacency list with a map mapping a bunch of point values to lists of point values as its adjacency list for each key. Okay, so now we're going to go over connected. Here's my connected method. So I decided to use depth first search, and I use that using a stack. So we have a new hash set, which is called visited to represent the nodes that we've already visited, so we don't like follow cycles over and over again. And then a new stack to use in our DFS. Okay, so first we push on the start. We push on P1, the start point, the start city. And while the stack is not empty, we keep visiting, doing the stuff in a loop. And so the current point will be the topmost point on the stack. So this will be like kind of like the most recent thing, because stacks are um kind of like first in, first outs. Yes. Oh, like last in, first outs. Excuse me, last in, first outs. Yes. And so if visited.contains cur is not true, so if we did not visit current yet. So the most recent node, if we did not visit, we add it to the visited list because we just saw it. And then for its neighbor, if visited does not have the neighbor, we push the neighbor onto the stack. So we're pushing current neighbors onto the stack. And then eventually, if we let this algorithm run, it will basically give us a traversal because we will eventually be traversing across the whole graph and seeing if P2 and P1 are connected. And the way we see that is if P2 was visited at any point during the traversal. Okay, so now we'll be going over time and space complexities of my approach. So DFS's time complexity is not amazing. As you can see, there's kind of a loop inside of a loop. So I suspect that would at least be n squared. But I chose also to do DFS because it's a little bit more intuitive to me rather than BFS, even though the switch would be quite easy to do, just switching the stack for a queue, and that would basically work. But yeah, let's demo it now. So let's do a graph demo. Sorry, excuse me, I don't know how to. Okay, here we go. So choose start city. Let's do Durham, North Carolina. And then end city, I'll do my hometown, New York, New York. And as you can see, there is a shortest path. This should be the shortest path from Durham to New York. Okay. And so we go back. So basically, I think that my implementation was really standard besides the fact that maybe I used a DFS rather than a BFS. And maybe in some cases a BFS would be a little bit more time efficient. But I really learned about a DFS, BFS, traversing through graphs, how to traverse through graphs in the different ways, and definitely Dijkstra's algorithm as well, which I haven't really discussed today. But I would say the biggest challenge was definitely figuring out Dijkstra's. That was very difficult, as I've never seen it before. But yeah, this project was really fun, and thank you so much.